In my opinion, gravitational lensing is the most amazing astrophysical phenomenon in the entire universe. And I came to that conclusion after my 2022 summer internship, where I worked on modeling the strong gravitational lensing of a Type 1a supernova by an elliptical galaxy. So today I'll give an overview on gravitational lensing, explain how it's such a cool phenomenon, and explain how it's such a powerful tool for astronomers to discover more about our universe, whether we're talking about discovering exoplanets or the expansion rate of the universe. A gravitational lens is a celestial body between a distant light source and an observer that is capable of bending the light from the source as the light travels towards the observer. We often see multiple or magnified images as a result of the lensing, as well as the weird distorted shapes that are pretty familiar to most people when they think about gravitational lensing. This celestial body can be pretty much anything. It can be a planet, it could be a star, it could also be a galaxy or a cluster of galaxies. And there are three main types of gravitational lensing. We have strong lensing, weak lensing, and micro lensing. But first, I'll talk about strong lensing. So with strong lensing, the lens is a large mass, like a galaxy or cluster of galaxies. And the deflection of light is also quite large. The alignment between the observer, source, and lens is favorable, meaning they're more or less in a straight line with respect to each other, leading an observer to see two or more separate images of the source. Then we have weak lensing, which is a comparatively weaker effect. Weak lensing can only be observed by looking at the shapes of numerous galaxies that show preferential alignment in one direction, indicating lensing. There's no single source or lens, but many background galaxies acting as sources and many foreground galaxies acting as lenses. Then we have microlensing, where the lens is usually a small mass like a star. The mass is small, so the Einstein radius is also small, meaning we don't see multiple images. Instead of seeing multiple images, the image of the source appears brighter for the duration of the lensing event. For example, a star will brighten if a sufficiently massive planet transits it. You may already have ideas of how gravitational lensing may be useful, but let's look at how gravitational lensing happens in the first place. So we have a huge mass, and somehow light is bending. But why? In classical physics, in a vacuum, light moves along in a straight path at the speed of light. This is because a straight line is the quickest and shortest path that light can travel. And light always takes the shortest path. However, according to general relativity, gravity can be described as a distortion of space-time due to the presence of mass. So in other words, space curves. So the quickest path now isn't actually a straight line in curved space. This quickest path is also now a curved path. So for light, we like to say that it travels along a path known as the null geodesic. This essentially means that in a curved space-time, light travels the shortest possible distance, the same way it does classically, but now in general relativity, we're talking about a curved space. The more mass there is, the more that space-time is distorted, so the path that light will take is dependent on the mass, hence the various different lensing effects that we see and the distinction between weak, strong, and micro lensing. So it's the very presence of mass in the universe that causes light to curve. Of course, for this effect to be noticeable, we need quite a lot of mass though. Gravitational lenses have many uses. For example, they can be used to measure the masses of galaxies and galaxy clusters, allowing us to find out where dark matter resides and how much dark matter is within a certain galaxy or galaxy cluster. This is obviously of great interest because dark matter is probably the biggest mystery in the universe alongside dark energy. Dark matter doesn't emit or absorb light, but it still has mass. Therefore, we can detect it, quote unquote, by studying the gravitational lensing patterns caused by the distribution of mass in the foreground. By quantifying the gravitational lensing effects and understanding the contribution of visible matter, astronomers can then estimate the mass of dark matter associated with a particular system. Gravitational lenses can also be used to find exoplanets through weak lensing. Say we have a planet and its host star aligned with a distant background star. When the planet passes in front of the background star, it acts as a gravitational lens and magnifies the light from the background star. Astronomers monitor the brightness of the background star over time. And when the planet and host star are aligned, the background star appears temporarily brighter due to the magnification caused by the planet's gravitational lensing. By observing this brightening event, astronomers can then infer the presence of a planet. Ideally, we'd want to observe a brightening happening multiple times just so that we're sure that it's a planet rather than maybe just one object passing in front of the star. And if you see it periodically, the same brightening event with a regular spacing, then we're even more confident that it's actually a planet. And somehow, as if that wasn't enough, gravitational lensing can also help determine the expansion rate of the universe. This is done with a technique known as time delay cosmography. So, gravitational lenses can create multiple images of a single distant object. These images can be observed from Earth because the light takes different paths around the massive object, resulting in different arrival times. And since the multiple images are created at different distances from Earth, each image takes a different amount of time to reach us. The time delay between the arrival of different images depends on the expansion rate of the universe, represented by the Hubble constant h0. And since the Hubble constant describes how fast the universe is expanding, an expansion rate of the universe can be arrived at. So these are the three main ways gravitational lensing is used in astronomy, and the three most exciting ways for sure. If you want to learn more about gravitational lensing, you can read all the links I have in the description below. I also have my Twitter, TikTok, and website in the description, so feel free to check those out, ask me any questions, and I guess I'll see you next week for another episode of me talking about astrophysics.